Welcome to the fifth part in the time series course. Today, we will continue with our non-stationary asymptotics. But unlike last week, where we worked with IID errors, we will now allow for serial correlation. And this will result in two new unit root tests, as mentioned here on the slide, the Phillips-Perron test and the augmented Dickey-Fuller test. Lastly, we will also zoom into the so-called spurious regression problem. Now, I've summarized the corresponding literature for today on this slide. While Hamilton includes the full exposition, today we will look at simplified cases as this is more important to grasp the intuition. So last week, we looked at our unit root test when we assumed our errors to be IID. Remember, we looked into the random walk model without drift, whose model equation is given over here. This week, we will again look into our unit root test, but relax the assumption that the errors need to be IID. And just like a couple of weeks back, we know that we can deal with serial correlation in the errors, either by correcting for the long run variance, which will give us the so-called Phillips-Perron unit root test, or by including lags in our model, which will give us the augmented Dickey-Fuller test. So let's start with the Phillips-Perron test. In our new setting, we still have the random walk model without drift, and we set the initial condition equal to 0. So nothing different here compared to last week. But now I explicitly write out my error terms ut, not as epsilon t, to allow for serial correlation in the errors. So I work instead with a linear process for the error terms ut. And I know that I can express this guy through a lag polynomial psi L that operates on my IID error epsilon t. So in other words, I can write my errors ut as an infinite sum of the IID errors, the epsilons. We will also need a bound on the coefficients, which is stronger than absolute summability, but it is satisfied by any stationary ARMA process. Now, what changes when we allow the errors to be serially correlated? Well, as in week 3, we will analyze this linear process via the Beveridge-Nelson decomposition. And this decomposition tells us that we can rewrite the lag polynomial as the difference of psi1 and the difference of a new lag polynomial psi tilde L. Why do we rely again on Beveridge-Nelson? Well, we do that because we managed then to break up our sum in two parts. One, where we have the sum of our IID errors popping up. And the latter part is nothing more than a scaled difference between our last and first new error. Now, from our derivations a couple of weeks back, we know that this last term is asymptotically negligible. And so that means that if we want to obtain the limiting distribution of this guy over here, we only need to take care of the limiting distribution of the first term. And this is nice. Why? Well, this is nice since it is made up only out of IID errors. So we know that this term, this first term converges in distribution to a normal with asymptotic variance sigma squared, the variance of the IID errors. And then we just need to pre and post multiply by the probability limit of psi1, which is nothing more than psi1 itself since it's scalar. Remember from lecture week 3, we called this asymptotic variance the long-run variance, and we used the notation lambda squared for it. So I can alternatively rewrite this result where I introduce the lambda notation for the long-run variance, and I go back also to my Brownian motion notation. So I can alternatively express this result like this, where the last expression on the slide looks very familiar, or it should look very familiar, because we have a scaled partial sum process, but it's slightly different from the one that we used before, as denoted by the X star notation. Because we sum here over all errors the U's, not the IID errors, the epsilons. And this guy indeed converges in distribution to this limiting distribution, just a rewritten version of that guy. If we would now again work with the R notation for our scaled partial sum process, where R is the fraction of the sample over which we sum, and we define here the scaled partial sum process, we would expect that the functional central limit theorem gives us this uniform convergence result, which is indeed also correct. Now that is all very good news. Why? Since it means that we can simply repeat all steps from last week by using the functional central limit theorem that now takes the long run variance lambda squared into account. Note that in Hamilton, there is a list of limiting results as summarized in these propositions. As the exam is a take-home exam, you are of course allowed to make use of these results. This can be reassuring to know what the limiting distribution needs to be, but realize that I might explicitly ask you to prove, explain in detail how you arrive at these limiting results. And of course, that is not written out in Hamilton. You will only be given points then on your assignments or your exam if you do know how to write out these derivations. So to illustrate these derivations that take the long run variance into account, let us go back to our case from last week, where we have the random walk model without drift. And we estimate also a model where we don't include any deterministic components. We are interested in testing still the null hypothesis that rho is equal to 1. But now realize that we have the error ut, which exhibits serial correlation, of course. The first step is still to start from the least squares estimator, plug in the DGP, and arrive at this key expression where you have estimator minus true population parameter expressed over here like this. Now that should really be very simple by now. Verify these steps for yourself. The crucial next step then is to introduce the appropriate scaling in the numerator and the denominator of this expression over here. And then we combine the terms in T to determine the asymptotic rate of convergence. In other words, the power of T by which we need to blow up this difference. What are your key building blocks to determine the appropriate scaling in numerator and denominator? Well, first, we need to rewrite our numerator and denominator in terms of sums of the UTs. Remember from the DGP that we know that y at time point t can be rewritten as the sum of the first t error terms to use. Then once we have an expression with partial sums of u's, we need to relate them back to our scaled partial sum process x star by writing out what this r is in a particular case, namely the fraction of the sample over which we sum. Once we have an expression with our scaled partial sum process, we can rely on the functional central limit theorem and the continuous mapping theorem if needed to obtain our limiting distribution. So let's have a first look at the numerator of this expression. I have rewritten the numerator over here, and apparently I need scaling by 1 over t, since I've put the correct scaling already on this slide. Let's see if we can find this back. First, rewrite the numerator in terms of sums of u's only. And I don't go over this in detail anymore here, since these steps are really identical to what we did last lecture week. So please have a look at them again. Once we have this expression, this guy over here needs scaling by root t in order for us to recognize a scaled partial sum process with r equal to 1, since we sum over all time points. And we know that the square of the scaled partial sum process converges to the scaled standard Brownian motion, which is also squared. For the last term, we need scaling by 1 over t, because the law of large numbers will simply tell us that this guy goes to the expected value of the squared errors denoted by gamma naught. So indeed, 1 over t is the scaling we need for the numerator, and we have derived its limiting distribution. Which scaling is needed for the denominator? Apparently 1 over t squared, since I've written it here already, but let's verify this. We start by rewriting our yt minus 1 term as the sum of all the u's until time point t minus 1. If we would have here a factor 1 over root t, we would then be able to rewrite this as our scaled partial sum process, where r is t minus 1 over capital T, since we sum the first t minus 1 observations. Now, why is there an additional factor 1 over t needed? Well, we recognize here a Riemann sum with this as the left endpoint, and 1 over t is nothing more than the width of the interval. Think back of the picture of the scaled partial sum process here from last week, being a piecewise constant function, and have a look at the slides from last lecture week again to verify that the same steps are needed here. And then just combine functional central limit theorem with continuous mapping theorem to derive this limiting distribution as written on the slides. So the numerator needs 1 over t, the denominator needs 1 over t squared. If we put these appropriate scalings there together, we see that we have asymptotic rate of convergence t, and I've copied over already the corresponding limiting distributions for the numerator and the denominator on this slide. Now let's have a closer look at this expression. First, what would happen to this expression when ut would just be the IID error, so the case from last week? Then naturally, we should arrive back at the expressions from last week that we derived. So let's verify that. What would gamma naught be in the IID case? Well, from the definition of gamma naught is nothing more than the expected value of the squared errors, the u's. If the u's are IID, then the UTs are just immediately equal to the epsilons. And this would be equal to the variance of the IID errors, since the expected value is 0. What would lambda be? Remember, lambda squared is a long-run variance. Well, lambda is then just sigma times psi1, which is nothing more than the infinite sum of the coefficients in the NA infinity representation of the errors U. But when the errors U are IID errors, there is no NA infinity representation. Psi naught is then simply just equal to 1, and all of the other psi's are 0. So this guy also simplifies to sigma. And when you plug in the expressions then for gamma naught and lambda square in the IID case, all the sigmas will cancel out and only the Brownian motions would be left. So we would indeed have exactly the same limiting distribution from last week. In other words, when we allow for serial correlation, the limiting distribution is different since the short run variance and the long run variance now both pop up in the expression and they do not cancel out because they are not equal to each other. The next question is then how to conduct inference. Well, last time we simulated from the limiting distribution, which we could do since it was only built up from standard Brownian motions. But this time, it also includes so-called nuisance parameters, lambda and gamma naught. And we do not know what their values are. So we cannot directly simulate from this limiting distribution. So we have a problem if we use this guy as the test statistic, we cannot simulate from its limiting distribution. But would the same problem pop up when we work with the regular t statistic? Well, let's study that in the next video.